In this video, I'm going to be explaining time response, all that you need to know to prepare for your time response exam under control theory. So, time response is simply the study of the behavior of the output of a system with respect to time. It's simply time response studies the behavior of a system's output with respect to time. And it also studies the output in terms of transient response, in terms of transient response and steady state response. For me, the transient response is the initial phase of time response, while steady state response is the final phase. Because transient response is actually the phase of oscillation before it enters into steady state, where it becomes, for transient states, I would say the oscillation varies, but for steady state is constant. That's what I can say. It's constant. Without wasting much of your time, for first order systems, to find C naught of t, which is the time response expression. Time response expression. If you are given an input, and a transfer function, g of s equal to 1 over ts plus 1, where t is a constant. The way you will know that is a first order is because the characteristics equation, the highest power is 1. This is the characteristics equation, and the highest power is 1, so it's a first order. In order to find C naught of t, which is the output, you'll be given the input and the transfer function in order to get the output expression to study the behavior of the output with respect to time. C naught of t is equal to inverse Laplace transform of g of s c of s. What this means is that you find the Laplace transform of the input given, then before you can now proceed with the transfer function and get the output from the product of g of s and ci of s and getting the Laplace transform. So getting the inverse Laplace transform, you get your output expression. Very simple. For second order, systems, to find C naught of t, which is time response expression, when you are given an input and transfer function g of s equal to k, which is also a constant k, divided by t s squared plus bs plus k. You can see that from the characteristic equation, the highest power is 2, so it's second order. So given these two things, the inputs and transfer function, to get this, first you convert for second order. There's just a small thing you do first before you can now get it. You convert g of s to the standard form. There's a standard form for second order system, which I will show you. Now, the standard form is g of s equal to w divided by s squared plus 2 zeta. This is zeta wn s plus w subscript n whole squared, and zeta, which is the damping ratio, is equal to b. Let me do it this way. Is equal to actual damping over critical damping. And is equal to b over 2 root tk from the original equation given. You get it. You'll be given this characteristic equation, so you get your values from there. Then we have w subscript n squared equal to k over t, and we have 2 zeta wn is equal to is equal to b divided by t, which is still equal to 2 sigma. Now sigma is equal sigma is known as attenuation, and w subscript n is undamped is known as undamped natural frequency. So after converting the equation, the transfer function you are given to the standard form, then you can now solve for, you can now get the time response expression for the second order system after converting the transfer function given to its standard form. Still using the same formula for first order, but just the difference is just in the fact that you have to convert this to the standard form, this transfer function given to you in your problem. So moving forward, for second order systems, we also consider the transient response specifications. For transient response specifications for second order systems, we consider the transient response specification. Now the first specification here is the rise time. The rise time is calculated. That's the formula. T subscript r for rise time is equal to pi minus beta divided by w subscript d w subscript d is equal to wn, which is the undamped natural frequency, root 1 minus zeta squared, and beta is equal to tan inverse of root 1 minus zeta squared over zeta. The second specification is peak time. T subscript p, this is pi over w subscript d, and we already know the value of w is w subscript n times root 1 minus square root of 1 minus zelta squared. The third specification that you'll be asked to calculate is the maximum overshoot, MP. This is equal to exponential minus zelta over square root of 1 minus zelta squared times pi times all times 100. This times 100 is in percentage. This is in percentage. Maximum overshoot is also called peak overshoot or percent overshoot. Is also called peak overshoot or percent overshoot. These are the terms you will see if you don't see maximum overshoot. For the last specification, settling time. T subscript S. Transient state response. The oscillation varies, but once it gets to 2% or 5% of the final value of the output response and remains constant, the time taken for it to get to that point is known as settling time. Now we can continue. So time for it to get to 2% of the final value is this formula here. Two percent criterion, 2% of the final value. Then for 5% of the final value, this will be 3 zelta W subscript N equal to 5% time taken to get to 5% of the final value. Now this is basically all you need for your exam. I don't think there is any other thing unless for the advanced part, but there's nothing else you basically need to pass your exam. So thank you for watching this video. Don't forget to like and subscribe to this channel for more videos like this. In my next video, I will be solving a problem under this topic.